Ever seen those cool, trippy animated battle backgrounds in old school games like EarthBound and thought, how on earth did they make that? Today, we're going to break down another trick from the retro graphics playbook, Horizontal Oscillation, and we're going to see how we can create this effect using WebGL. It might look like a complex, expensive effect, but the core idea is actually really simple. Imagine taking an image and pushing its pixels left and right in a smooth, wave-like motion, like a sine wave. By using this effect, it'll make our image look distorted. And then by moving that sine wave over time, it'll give us this nice animated effect. Remember sine waves from math class? They're smooth, repeating curves that go up and down. We can use that wave as instructions for each horizontal row of pixels in our image. The wave is going to tell us how far to push them left or right. So if we take our original sine wave and we turn it, and then if we place it on top of our texture, this will be our instructions for where to move our pixels. So as an example, if we take our texture here, and we apply our sine wave on top of it, for each of our rows of pixels here, this white line is going to be the original position of that pixel, and our sine wave, this blue line, is going to be how far we need to move that row of pixels over. By applying that to our original texture, we get this effect here, where each row of pixels is now shifted based on our sine wave. And so at our wave's peak, all of our pixels move to the far right. At the throw, they move to the far left. And then in the middle, our pixels don't move at all. When applied to every row in our texture, you get this beautiful wavy distortion. But right now, this will just be a static wave. And to animate it, we just need to update our sine wave over time so our wave will move, which will create this distorted effect here. We can do this by feeding a constantly increasing time value into our sine calculation inside our shader. This makes the wave slide across the image, causing our pixels to wobble left and right smoothly. And we can even tweak how it looks. By adjusting our amplitude, we control how far our pixels will move. By changing the frequency, we decide how many waves will fit across our image. So really, the image isn't bending or warping, it's just sampling from shifted pixel coordinates based on the sine wave. A simple illusion, but a powerful way to add natural, organic motion. To recap, a moving sine wave guides how far to push each pixel horizontally, creating a smooth oscillation. It's a fantastic shader trick to add dynamic energy to your scenes with minimal cost. Now before we build this with WebGL, let's quickly review our sine wave. A sine wave is basically a smooth, wavy pattern that goes up and down over and over again. This smooth wave pattern shows up all over in nature, in water, sound, light, and in motion. And for our sine wave function, there's 4 basic parts. First, our A, or our amplitude. This is to control how tall our sine wave is. When our amplitude is set to 0, we just have a straight line, but as this value increases, this will control the height of our sine wave. Next, our H, this is our horizontal shift. Our horizontal shift is going to move our sine wave along our graph. Our B value, this is our horizontal stretch or our compression, and this controls the period of our wave. And our period is how long it takes us to complete one cycle. One cycle is when we take one point in our graph, and we go until we reach that point again. So if we start at our center on our sine wave, it would take till 2 pi to complete one cycle. So when this value increases, this is going to stretch out our sine wave, and so it's going to take longer to complete one cycle. As this value decreases, it's going to compress our sine waves, and so we'll complete more cycles within that given period of time. I like to think of this as like a spring, and we're squishing it down, so we get this effect here. Our last value, our K, this is going to be our vertical shift, and so similar to our horizontal shift, this will just move our sine wave up and down. So now to create our effect with WebGL, we currently have code set up to take in a texture and then just render out that texture. In my example, I have 4 different textures, so by choosing a different index for my texture, I can render out these different images here. For our effect, we'll need to have a few different variables to control our sine wave. So let's add in float. First we're going to have a speed for our animation, so we'll do U speed. We're going to set this to 1.0. Now we'll need to do our amplitude and our frequency, so let's do float. We'll do U amplitude, and then we'll do U frequency, and we'll do 25. So now to build our wave effect, we're going to use our built-in sine function. So let's do float, we're going to call this wave, we'll set equal to our sine, and now we want to take our Y position of the pixel that we're currently processing, so we're going to have our UV, and then our Y. We want to multiply this by our frequency, So our sine function, this is how we can create our sine wave to create that smooth, wavy effect. You can think of sine as a machine that'll take any input, like our position and our time, and turn it into a wobble. If we want something that goes smoothly left and right and up and down or in a circle, we want to reach for sine and cosine. How our function works is we can take any value in radians, and our sine function is going to calculate a value between 1 and -1. If we graph out all of our possible values on our circle here, that results in our sine wave that we were just looking at. So by using our built-in sine function, that's going to give us our value here on our sine wave. Now that we have our sine wave value, we need to calculate our offset for how far we need to move our pixel. So we're going to do a float, we'll do offset, we're going to set it equal to our wave, and we want to multiply it by our amplitude. Now that we have our offset, we need to calculate our new vector2 position for our pixel. So we're going to do our vector2, we're going to call this new chords, and we're going to set equal to our vector2. So now for our horizontal oscillation, we only want to move our x position on our pixel, we want to keep the same y value. Since we're just shifting our row, so we're going to use our UV, we'll take our x value, we want to add in our offset, and for our y value, we'll just use our original y. And now with that new position, we want to sample that from our texture so we can render that out. So for our out color, we're going to set this equal to our texture. And now for our texture function, we need to provide our sampler. So this will be our U textures. We'll use our 0 index. And now we need to provide our vector2, and so this will be our new coordinates. Now if we save, right away, we'll see our image now appears to be distorted. And so now if we modify our frequency and our amplitude values, this is going to modify our sine wave that we're creating, which gives us a more distorted effect. And so we can kind of see our sine wave here, and how we modify those values changes that sine wave. So now to add in our animation, we just need to modify our sine function and our value we're providing here. So we'll want to take our original value, and we'll want to add in an offset to have this value move. For that offset, we're going to take the amount of time that has passed since our shader has compiled or started running, and then we're going to multiply this by our speed so we can control how fast it'll move. Once we do that, we now get this nice smooth animation effect for our texture. And by modifying our speed value, this is how fast our sine wave is going to move through our texture. So here's a recap of what's happening. For each pixel, we calculate a sine wave value based on its vertical position plus the elapsed time. That sine value is going to determine how far we shift our pixels horizontally. We then sample our original image at this shifted coordinate, producing this wavy effect here. Because this runs entirely on the GPU, it's super efficient, perfect for games, demos, or any scene that needs some subtle, natural motion. And that's the Horizontal Oscillation shader in WebGL. A simple idea with beautiful results. In the next video, we'll plug this shader into Phaser 3 and make it game ready. Thanks for watching. If you found this helpful, please give it a thumbs up and drop a comment with any shader effects you want to see next. And if you want to support the channel and help me keep making tutorials, I've set up a Ko-fi page. The link's in the description. Every coffee helps. Don't forget to subscribe so you don't miss the rest of the shader series and more Phaser tutorials. See you next time.